Welcome to UW Chemistry 237, Chapter 3 Notes. Today we're going to cover acid-base chemistry and other important techniques. Before we begin, there is an important thing I have to cover. While editing Chapter 2 video, I almost fell asleep. It was like an hour and 40 minutes long, so it was really boring and hard to understand. So what I've decided to do is instead of making like 2 hour long videos, I'm going to break each chapter down into different parts. So it's more fast paced. The content is easily and more clearly like grouped together. This way you won't have to sit through almost basically a class lecture. I'm trying to make this in a way where it's faster, and so I'm going to make sure that my content reflects that. So shorter pace videos coming in the future. I'll be breaking chapters down into smaller sections. So with that out of the way, let's start our chapter. So let's begin with Lewis acids and bases. So what's a Lewis acid? A Lewis acid is a compound. Let's start our chapter. So let's begin with Lewis acids and bases. So what's a Lewis acid? A Lewis acid is a compound with electron deficiency. So naturally, it accepts electrons. Some examples are tetrabutyl ion, sorry, third butyl, not tetrabutyl, third butyl ion, right? Another example is bromine trifluoride. Another example is bromine trifluoride. You can clearly see that this carbon doesn't have an octet, neither does this boron. So these are both lacking electrons, so they really want these electrons. They're Lewis acids. The next thing, on the contrary, a Lewis base compound is a compound with excess electrons. So naturally, it donates them. So examples of this would be a chloride ion, OH minus, and ammonia. This is a big one. Ammonia comes up a lot in organic chemistry. So clearly these all have extra electrons that can be used to make bonds. So um, next thing we're going to cover is a technique. And this technique is called curved arrow notation. So in my first chapter 1 video, I did cover a lot of curved arrow notations, but it is formally introduced in this chapter, so I'm gonna talk about it really quickly. So first thing you have to know is it indicates the flow of electrons, indicates the flow of electrons. It helps us track, I mean, might as well just put down it helps us track electron pairs in a chemical reaction. Some things you need to know is that the charge of the reactant and product don't change. So if the reactant started with a negative charge, you'd end with a negative charge. If you're neutral, right, then you'll end up with a neutral, something like that. I'm gonna erase this. Let's see. Um, yeah. So an example of this would be a fluoride ion, which we know is a Lewis base, right? Interacting with a boron trifluoride, right? So the main thing you need to know for this is rich. The main concept is rich, give, and poor. I said rich, give to poor. If you're electron rich, which makes you a Lewis base, you will give the poor, which is a Lewis acid. So you take these two electrons, you show their movement, an arrow, the flow of these electrons into the, all right, so this is your arrow mechanism, your curved arrow mechanism, and the product would look something like this. I would like you to see how the charge is conserved here. So you get tetrafluoride ion. So rich go to the poor. This is a great example of a curved arrow mechanism. So another thing we have to cover is to make sure that we're covering all different kinds of reactions. So in organic chemistry, not all reactions, not all reactions have a clear cut electron deficient ion or compound. So I can't write that. These reactions are called electron pair displacement reactions. And so we're gonna cover them. So the other key concept that you need to know is to gain something, you have to lose something. It's dying the edge here. I'm probably gonna rewrite this part so it doesn't look so horrible. Something. Um, so with these displacement reactions, for example, you have ammonia and methyl bromide. So what happens is, oh, before I cover this, I have to cover some naming conventions. So if we move back here, so we have to cover terms like nucleophile and electrophile. So what is a nucleophile? Philia is to love. So if you're a nucleophile, that means you love the nucleus. If you're an electrophile, you love the electron. So if you love the nucleus, right, you probably have to have a negative charge because nucleus is a positive charge and opposites attract. So you are electron rich. So a Lewis base. If you love electrons, that means you have to have a positive charge. That means you're electron poor and you're Lewis acid. So you want what you don't have. These are all life lessons too. I mean, I'm not gonna lie. Rich give to the poor, and to gain something, you have to lose something, and you want what you don't have. Grass is greener on the other side. These are all lessons in life, I guess, and they apply really well to organic chemistry as well. So where was I? As I was saying, right? You have your sorry. So in this case, now I'm gonna just replace Lewis acid, Lewis base with just nucleophiles and electrophile. So this guy is your nucleophile. Also Lewis base. Just for this problem, I'm gonna write them as both. This guy is your electrophile. Now you might ask me why this guy is an electrophile. It has a full octet and everything. Think about the charge here, right? This bromine is very electronegative, highly electronegative. So what it does, it creates polarity. So you have a partial positive here and a partial negative here. So the electron density looks something like this. So in this case, the carbon is the electrophile, but it really isn't proper electrophile because it's just partial charge. Think of it not as a poor person, but like middle class. So in this case, what happens is the rich or a benefactor is supporting you, gives you its electrons, and then you have to kick out your previous benefactor. So in this case, what happens is, I'm messing up all the colors. So this is a reversible reaction. So what happens is you form a bond with the ammonia and you kick out the bromine. This is called a leaving group, by the way. This is a leaving group because it leaves. So it's in the name. It's a leaving group. All right. So what happens in this reaction, right? So the ammonia, which had excess electrons to give, attacks um, the electrophilic carbon because of the polarity created by the bromide due to its electronegativity. which creates the attack. And in this case, what happens is the electrons in this bond, since bromine is so electronegative, it just keeps it. And when it keeps it, it is able to hold onto it and it's stable. So bromine being so electronegative is able to hold on to the electrons it gains from losing the bond to the carbon. So that's why it's okay being a leaving group, if that makes sense. So you have two kinds of, so the two main lessons from this is, bear with me. So the first rule is rich give poor. Source to an acceptor. In this case, a nucleophile to an electrophile. Lewis acid, oh sorry, Lewis base with Lewis acid. The second is breaking. This is the one, by the way. This is example of rule 2. So breaking bond and giving electrons the more electronegative element. So in this case, that would be bromine. Another example, this one is hopefully much neater. You have an anion, like this one. Then you have your neutral compound. It's looking for iodide, right? So which one is nucleophilic? It would be the oxygen. Which one is the electrophilic one, right? Because you have, this is electronegative, highly electronegative. So you have again this, or you have a partial negative charge, partial positive charge, right? So this becomes, so this is your nucleophile. This is your electrophile, right? So rich give to the poor. So this guy attacks the carbon. Remember, make sure, yeah, I was gonna make that mistake right here. So I want you to learn from it. Never, okay, so the electrons will always go to the carbon. Okay, if you draw something like this where it's pointing towards the hydrogen, that's wrong. So majority of the professors will take points off for that. So you want to make sure. Another thing, yeah, so the arrow starts at the oxygen's electrons and then ends up at the carbon right here. That's your first arrow, right? So the rich giving to the poor. And since this guy is like the middle class, not really poor, like I would say, um, this carbon would be like poor, electron poor. Like this guy is mostly like middle class. So I would say in terms of hierarchy, right? So if you're gaining one benefactor, you're gaining something, so you have to lose something, which is this iodine. And this iodine is fine with leaving the carbon because it is electronegative. It can hold on to the electrons and it is stable as an ion. And it's fine being an ion. So at the end, what you get is, wait, this both ways, by the way. So reversibility plays an important role. CH3, OCH3, which is a ester plus an iodide. Another thing I want you to notice is the charge always stays the same. It was negative before in the reactants and it's negative in the product. Same thing here. It was neutral in this reaction, neutral in this reaction, and it's neutral here as well. Even though like the complete reaction is neutral, not individual compounds, but the complete reaction is neutral, right? The amide and the bromide together cancel each other out. Same thing here. So with the reversibility of a reaction, what happens is it switches back and forth. Reversibility of reactions switches their names back and forth, right? So if we take the same reaction again, CH3, O minus plus CH3I, going this way, going back, CH3O, CH3 plus I minus. All right, I'm gonna do these in two different colors. So if you're going from left to right, right? So this guy is your nucleophile, this guy is your electrophile. Um, Again, so iodide would be your leaving group, right? Leaving group here. So electrophile, nucleophile, iodide leaves, right? In this case, nucleophile, electrophile, and this is your leaving group, right? So in this case, so when you go backwards, what actually happens is the iodide now becomes the electrophile. Sorry, the iodine becomes the nucleophile, the carbon becomes the electrophile, and the oxygen becomes the leaving group. So the designations switch. Mostly between the nucleophile and the leaving group. But yeah, it is important to know. This is your leaving group. So when reactions are reversed, the nucleophile and the leaving group switch their names. So you can write them back and forth. So that is basically that. Next thing we're going to cover is curved arrows with resonance. This is also something I covered in the first video. Uh, right now that we know more about nucleophiles and electrophiles, things like that, we can designate these values. All I want to say is in a compound, something like this, nitro CH3N O minus plus charge. In nitromethane like this, right? You can say that this guy N is the electrophile, right? And the oxygen is the nucleophile. But you can like in your head, I want you to think about this in your head. Do not actually write it down because in a singular compound, each atom cannot be a nucleophile, electrophile. You can have electrophilic sites, but not like electrophile or nucleophile. So like mentally, you can take a note of like where the electrons are going to move because it goes from high to low. But like do not label them as nucleophile or electrophile. But I'm doing it just for like clarity purpose, right? So it goes from rich to poor. In this case, the rich is the oxygen and the poor is the nitrogen. So you have the bonds moving here. In this case, what happens is the double bond is basically like the p orbital is just electrons, the extra electrons. So the electrons are obviously rich, right? Electrons is the currency. So in this case, electrons are rich and then they move to the oxygen in this case, which is poor because it's neutral. So you can then move, right, CH3, then you're left behind an O plus charge here, and then a minus charge here, right? But like we covered before, these are both like false, like mythical forms. These are both mythical forms, like remember dragon. Sorry. This is the dragon form. This is the unicorn, right? The mythical forms. But in actuality, in real life, what you would see is something like this, right? With partial positive, and these are partial negative charge. Actually, this is always positive regardless. So positive charge, and these two are negative charge, right? And this is your rhino, the real existing. I'll say this is the real existing. This is the resonance structure. And these are your like resonance forms. These two are your resonance forms. Same thing can happen like on this side, right? You can this high electronegative, right? Donate electrons, pick up electrons, and then you can go back this way. As you can switch between the rhinoceros and dragon form, but we know the true form is the resonance structure. Right, so yeah, that's pretty much arrow movement for this is your curved arrow structure with resonance. I will do a couple more examples because I feel like those are important. Some more examples. Okay, let's do this one. Right, you have something like this. So like we said before, double bonds are basically just electrons shared between carbons, right? So the orbital just has electrons, so you can take the double bond electrons and give it to the cation. So what happened? So what happens? It moves. right? So now you have this guy, right? And then same thing can happen here. You can take the double bond, share it with this carbon. Oh, this arrow is misleading. I want to make sure you guys don't, like I said, make sure that's pointing to the carbon in both cases, right? I'm making it fairly obvious. So, and then you have your double bonds again here. Boom. So you can see how the resonance structures can move from all the way to the right side to all the way to the left side. A more distinctly changing example would be something like this. Maybe something like this. So, right, these double bonds can be shared to the oxygen, right? Which creates this. Right, with a positive charge here. Next, what will happen is the double bond from here move down here. So you'd get something like this. Right, and the double one was here. Same thing. This double bond just moves forward, carbon, and you're left with this guy. So you can see how some resonance structures can like change functional groups completely. So you went with a key from a ketone to an alcohol. So that's also interesting with resonance structures. You can see how it can change functional groups altogether, going from a ketone to an alcohol, and with the arrow pushing mechanism. So with this comes energy stabilization, right? Important stuff, right? With going back to the rhinoceros and dragon form stuff, energy stabilization. Right, as we talked about earlier. Let's take another example. If we have something like this, CH3, I had too many carbon electrons in there. So this form going to this form, CH3, C, CH3. Oh, wait, I didn't draw the arrows. Whoops. Right, so this guy's the electron rich going to the electron poor. Now you have this structure, the single bond O CH3. Right. Now in this resonance structure, you can see that before you had an octet with the carbon, but then you shifted it and you got rid of the octet from the carbon and you moved it to the oxygen. So instead of in the first scenario, oxygen had extra electrons, but the carbon was in an octet. In the second case, you get rid of the extra bonds with oxygen, but carbon now doesn't have the exact amount of bonds that it needs. Before, oxygen wasn't in an octet form. Now carbon is not in an octet form. So how does this impact your energy? All right, you know this is your dragon form. This is your unicorn, right? And both are actually not real. Your real form is this positive. Right, and CH3. Yeah, this is also partial positive. Right, so this is your real form, which is the rhinoceros form, right? So in an energy stabilization concept, which one will have the least amount of energy, right? So let's mark them as 1, 2, and 3, right? So if you have your energy diagram back here, right? This is your energy. Which forms will have the lowest amount of energy? We know that obviously it's 3 because it's a resonance stabilized form. Now the interesting bit is between 1 and 2, right? Which one would have less energy, 1 or 2? In this case, it would be 1, and the most energy would be in 2. Why? Because in 2, you have no octet. You're breaking the octet between the carbon, between the carbon, while in this case, you have an octet with carbon, and the negative and positive charge is on oxygen. And since oxygen is electronegative, it is able to hold this positive charge much better than the carbon. So high electronegative, better able to hold the charge. So that's why it's less stable. So if I give you another example where you have CH3O, CH2 plus, right? Versus this one, CH3O, CH2, with this guy having a plus, right? Which one is more stable? Which one would be more stable? This guy would be more stable because you have carbon in the octet confirmation. Carbon is octet, and positive charge is on oxygen. And since it's electronegative, meaning that if you like draw this out, it's sucking electrons from both carbons, right? So it's something like this where you have partial positive, partial negative. Same thing here, partial negative, partial positive, right? So you can see that this is very negative space, so it can hold the charge better. So positive charge in oxygen, and it can hold it better, more stabilized. That's why this guy is better. So I'm just gonna erase this extra smooshy stuff up on there. There. That's why it's better. So same thing applies here. So an energy diagram, maybe change colors a little bit. 1, 2, 3, right? 3 is the lowest because it's resonance stabilized form, where the charge are not localized to a specific carbon or specific element. They're free moved. Uh, in number 1, or sorry, in 2, you have the positive charge on on a element that cannot properly hold that positive charge, so it's highest in the energy. And one is semi-stable because you have a positive charge on a mostly electronegative element. So like it has a partial negative charge already, and putting a positive charge helps the um, stabilize the charge, and so it's less in energy. So this is what all we're going to cover in this part 1, and we're going to continue with part 2 later. Thank you for watching.